Well, good morning, everyone. I want to start out by mentioning that if you look at your program, you'll see that the title listed for my talk is different than the title listed on my slide. And that's because usually when I write talks, they evolve over time, and the title I gave Kim and Carl a while ago is not where I ended up. So what I did, and I think the title should reflect where I ended up, I will still, as Carl asked, talk about motor patterns acquired early in life. But the twist I'm going to take on that is to focus on the brain behavior coalition that's emerging as skills are acquired. And I also want to focus a bit on context, because I think it's important for us to understand the context in which these behaviors are demonstrated in order to understand better how and why they are emerging. I also want to take this time to acknowledge my co-author on this talk and the paper we are writing, and that is Ryota Nishiori, who was a doctoral student of mine at the University of Michigan and who is now a postdoc at NIH. So we have three goals for our talk. First is to review briefly some classic motor patterns that emerge early in development. And second is to share data from some experimental studies designed to test theories about how and why these patterns emerge. Third, we're going to focus on what I like to call the final frontier for studying development of infants' motor control that has just begun to emerge via recent technological advances. That is the use of brain imaging techniques to document the emergence of cortical organization as infants perform functional, goal-directed tasks. I'm not suggesting that that's the only set of interesting and exciting questions to ask, but only now has that frontier begun to open for us, being able to look at brain activity during motor tasks in infants. So I think the number of questions, the types of questions to be asked is nearly limitless. I'm also showing Ryota on this slide because the data that I'm going to be talking about related to this point largely emerges from the work that he did with us at Michigan. So starting with classic descriptions of patterns observed early in life, I believe we need to start in utero. Development does not begin at birth. Development of growth and so on, and much less does development of neuromotor control begin at birth. And for classic patterns observed in utero, we turn to the work of Prechtel and DeVries and others who use 2D ultrasound to identify patterns emerging over the fetal lifespan. And what they showed is that early in the fetal life, you see simple patterns, head flexions, leg extensions and flexions, and over time, more and more complex patterns begin to emerge. Now, what they did was also link the emergence of those patterns with changes in neural maturation over that same time period, correlational data. Well, within that first trimester, as I said, some of the examples include head and trunk extensions and leg flexions. So early on, you see those patterns. That's a subset of patterns utilized by Van Meerendonk to actually challenge their argument that the patterns are simply driven by maturation of the nervous system. They examined babies' behavior, fetuses' behavior over longer time frames, but also in a more rich environment. They examined context, the fetal posture, the uterine contour. They looked at the impact of the amniotic fluid flow and the sequence of events as they unfolded. So again, just to sample some of the results they obtained, they showed that in supine, when the spine is flexed passively, fetuses will push with their legs to shuttle their body cranially into upright. When prone, spontaneously, fetuses will adapt to bulges in the uterine wall, bending one knee while pushing with the other knee and lifting the pelvis to climb over. They concluded what they found is adaptation. To quote, development of gross motor control in utero emerges in the presence of a dynamic and interactive environment. So moving forward in time, but still prenatal, we move into third trimester when more complex patterns are emerging. One of the classic patterns is hand-to-mouth behavior. Rieflin et al. Used very sophisticated 4D sonography now to study longitudinally the emergence of this pattern. They concluded that hand-to-mouth patterns emerge as a function of exploration, practice, and learning. And the way they obtained those data was to map the areas of the face and identify when and how often the hand contacted that face. Data showed that initially the pattern of contact was dispersed over the entire face. Over time, fetuses honed in on making that hand reach the mouth, and over more time, the mouth began to open in anticipation of contact of that hand. So already pre-birth, we're seeing evidence for exploration, practice, adaptation, and learning. Then a dramatic shift happens called birth. This change in context means that opposing the forces of gravity are more difficult. All the motor patterns that we see in utero will reappear at some point post-birth, but at this point in their lives, many of them are not observable. If you can imagine a 7.5-pound baby at birth on average that has 25% of its body mass made up of its head, we've got 2 pounds of head to lift against gravity. So it's going to take a little while for some of those to reoccur. In fact, few obvious self-initiated functional goals are observed at this point in time. So that all sounds negative. On the positive side, there are lots of new opportunities to explore, lots of new sights and sounds and contexts that we place them in. They begin exploring and identifying goals to achieve, they become very active, and in fact, very rapidly begin to acquire new skills. So I'm going to fast forward now to about 4 months. By this period, you're going to see a whole array of new skills. And as I go through these briefly, I want you to pay attention to the context in which we are observing these kinds of patterns. So by 4 months, babies will hold their heads aligned with their bodies when we hold them at our shoulders. They'll sit up for 30 seconds if we give them some support. They'll successfully reach for objects, especially when we provide trunk support. We put the objects within their arm's length, and we have a grip-sized object for them to reach for. They'll move their legs in a variety of hip, knee, and ankle patterns, especially when we have them on a nice firm surface for them to rest against. Fast forwarding again to 8 months, now we see another set of additional tasks that they learn to perform. They can sit alone with good control. They can roll over from supine to prone and from prone to supine. And they make forward progress in prone. Now, each of those might draw from your thinking some classic images of how they do that. But in reality, the coordination patterns used by babies to produce these 3 simple behaviors, simple to us, are very varied. So in fact, for forward progress in prone, you might think about hands and knees crawling or creeping. But babies don't come with a user's guide. What they do come with is about 200 joints and 650 muscles. In other words, many degrees of freedom. And in fact, they use those degrees of freedom to discover their own ways of moving, and very many variations are seen. In fact, Adolf and Verreiken published a paper in 1998 in which they identified at least 24 different coordination patterns babies use. Just a few of them are demonstrated here in these images. So describing behavior and classic patterns and hypothesizing what we think is going on and how those are being acquired takes us a little way down the road. But if we want to move further down as scientists, we need to set up experimental challenges to something like a maturational explanation for change. And one of the categories of maturational myth, I will call it, is that the emergence of control follows a cephalocaudal maturational process. In other words, we learn to pick up our head first and then push up our shoulders and use our arms and so on. Well, reaching is one of those behaviors that emerges in the typical environment at about 4 months. So it fits well into that notion. Fortunately, we have some very clever scientists, Audrey Vandermeer among them, whose group showed that even neonates, babies who are a couple of days old, can show us they have goals and can act on them, demonstrating self-initiated functional arm patterns. What you see here is the design they used, in which they have babies supine in their crib, arms are at their side, and there's a barrier between their head and their hands. So they can't directly see their hands, but there's a camera focused on the right arm in this case, and that projection is on a screen to the side of the baby's head. So when the baby moves its arm spontaneously, if it moves out of camera range, it can't see its hand anymore. If it keeps moving and the hand comes back into range, it can see it. Over time, the baby will keep that hand in view of the camera, unlike what the other hand is doing. And even with a small amount of weight on a pulley system, as you see shown here, that will tug the hand away from the camera's view, they will pull it back into view. Cole Galloway and colleagues did a series of studies in which they continued kind of on that theme, showing that when infants reach for objects at 4 months, it's erroneous for us to think that this is the first time they conceive of that goal and can control their limbs sufficiently to do so. They followed infants longitudinally, placing them in a context that made objects equally accessible to their arms and to their legs. Results showed that exploring objects and contacting them with their feet occurred a month earlier than with hands. Same goal, making contact with those cool objects that are out there in front of us. Uniquely different emergent patterns, however, set in motion by the context, their own muscle strength, the biomechanics of their bodies and the environment they're placed in, and the development of the nervous system as well. Well, in 2002, Rosa Angelo Kinsler, Esther Thielen, and I kind of ramped it up a notch, if you will, to test babies' ability, even at 3 months, to alter not just their behavior, but their coordination patterns. We studied babies in Roby Collier's classic infant mobile paradigm. Carolyn Roby Collier showed that if you attach a ribbon to the ankle of a baby that's laying in a crib, and the other end of that ribbon is attached to a mobile suspended overhead, they will discover that contingency and move that leg vigorously to get that mobile, which is very motivating, to move. We replaced that ribbon. Let me see if I can get this video to show you the context. We replaced that ribbon with goniometers that sensed when the knee joint angle triggered mobile activity, but it triggered it only when the infant knee passed through 85 degrees of flexion. Now, we chose that because we wanted to see if we could elicit vigorous kicks, and we thought we could use that then in clinical populations. What we found was babies all learned that contingency. They all learned the task. Half of them learned what we wanted them to learn, vigorous flexions. The other half outsmarted us. They discovered that the computer turns the mobile on as soon as they pass through that range, and they simply hovered right around 85 degrees. The point is, babies observed the context, generated spontaneous activity, discovered contingencies, and repeated efforts to achieve that goal and became skilled. 3-month-olds are more sophisticated and have better motor control capacities for learning than we used to believe existed. So moving on to the next level of basic science that I'd like to address, we're going to talk a little bit about brain imaging in infants. But I'd like to put that in context first. We know that motor patterns, even very early in life, are dynamic. They're influenced by context, by practice, learning, and goals. We know that the brain is also changing rapidly. It's growing, yet losing neurons post-birth, even as synapses are increasing and overt learning accumulates. We hypothesize, based on adult studies and principles of neuroplasticity, that the link between brain organization and action is goal-driven and bidirectional. But the empirical evidence linked to healthy human goal-directed efforts in infants has been elusive. Fortunately, we have now several brain imaging techniques that have been deemed safe and useful for documenting brain activity and change in infants. So magnetic resonance imaging is perhaps the one you're most familiar with. It's best known. It has excellent spatial resolution, can quantify anatomical characteristics that change with time, but as you might pick up on that image, to put a baby in the MRI tube, they either have to be soundly asleep or sedated. That means functional self-initiated behaviors are very difficult to achieve in that context. Then we have EEG, which has a long history of infant cognitive studies and adult motor learning, and only recently has begun to be utilized to test some motor issues. And my colleague Daniela Corbetta has a series of studies published in which she did some very elegant analysis of the areas of the prefrontal cortex and motor cortex as babies start to walk, to look for the influence of coupling arm movements on the development of laterality. Functional near-infrared spectroscopy has a long history of use in hospital settings to monitor brain activity in seriously ill babies. More recently, it has been adapted to study many brain behavior links across a wide age range, and very recently we've begun to utilize that with infants. In our lab at the University of Michigan, we chose to use FNIRS because it's less susceptible to motion artifact than EEG with better spatial resolution. It allows participants to move their bodies, to walk, to reach, and so on. And the number and placement of optodes is flexible, as is the headgear. All of these make FNIRS attractive for use with infants and attractive because it can be used as well across the lifespan. Now, our goals overarching this line of work are to document the co-occurrence and changes in self-generated patterns of movement and cortical activity in real time and over repeated cycles of behavior to uncover the temporal sequence of relevant changes in brain and behavior. That is, do our hypotheses hold or not at this level? Because we had new equipment and no other studies had documented infant brain activity during performance of functional motor skills, we took our first empirical step with adult performers. So we designed a study that would mimic the tasks that we wanted to use with infants to confirm that the technology could tolerate these levels of limb motion and confirm the sensitivity of this system, particularly our system, to detect changes in the motor cortex spatially and temporally relative to resting state. So we had adults sit at a table and reach for objects unimanually with the right hand and left hand and bimanually, and then we had them walk in place. And here you can see we had a 32-channel system that allowed us to have 18 channels of information going across the sensory motor cortex from the left to the right, and this is a top view. So what did our results show? We were happy to learn that our results supported the canonical contralateral cortical activity expected for unimanual reaching. So if you look at the top two figures, going from left to right, we have the sensory motor cortex from left to right with the 18 channels we were monitoring. And in adult reachers, we expect if you reach with your right hand, that areas on the left side of the sensory motor cortex will be active, and that's what we see. If you move down to the next one, when you reach with the left hand, the right side should be active. When we have bimanual reaching, you're going to have activation of both sides, plus in between you have trunk activity that it's stabilizing. And all the way down with stepping, we now see right and left sides because they're walking in place and using arms on both sides, but higher activity in the midline, which is where the trunk and leg areas are. We concluded from that FNIRS is sensitive enough to detect motor cortex changes between reaching, stepping, and resting states, and could tolerate limb movements for tasks that we plan to use for infants. In our first study with infant participants, we worked with healthy infants at 6 and 12 months of age, asked them to reach for grip size. Well, we didn't ask them. We teased them and motivated them to reach for objects that were grip size while seated, and we elicited stepping while supported on a motorized treadmill. Now, we chose those tasks and ages for specific reasons. At 6 months, reaching is clearly goal-directed, functional, but not fully stable. By 12 months, it's goal-directed, functional, and very well practiced. Stepping, on the other hand, at 6 months is elicited, not goal-directed or functional. They haven't been practicing walking. By 12 months, it is clearly goal-directed. They're walking or at least have months of cruising experience. It's functional but not stable. Here you can see one of our infants in the infant seat. We're monitoring his cortical activity as he's getting ready to reach for a cute little object. There he goes. And it goes into the mouth. On the right, you can see one of our infants being tested in the treadmill stepping paradigm. This is actually the headgear that we're using in the next study, but at least you can get a sense of what the baby looked like in this context as we're monitoring his activity. Okay, I know that's cute, but we got to move on. What you can see here is basically the headgear that we had to design. The headgear itself for infants we have to construct, and that was one of our early versions, but it did work, and you can see the sensors across the sensory motor cortex. The number of sensors was reduced from what we use for adults. Babies' heads, while large proportionately, are still small compared to adult heads. So we had 6 regions of interest that we could monitor across the sensory motor, or M1. We hypothesized that when novel goal-directed skills are emerging, diffuse areas of the motor cortex will be activated. As control increases, the diversity and range of motor neurons activated reduce. So what do we find? Here we have the results for reaching, and on the left side you have the data for 6-month-olds and the right 12-month-olds. When goal-directed reaching experience was relatively low, broad areas of activation occurred. So on the left you see 5 of the 6 regions activated, and activated at a high level, which you can see in the bar graph below. At 12 months, the number of regions activated significantly reduced and becomes more efficient. And again, the level of activity is lower now. It's fewer neurons and not as high level of activity. For stepping, same organization as the previous slide. At 6 months, when steps were elicited and did not reflect patterns infants had previously attempted, motor cortex activity was low. Low in number of active areas and intensity. By 12 months, as skill emerged, cortical activity significantly increased, activating a larger area and more intensely. So the conclusions from the first infant study were as hypothesized, based on neurodevelopmental theory and the inherent plasticity attributed to all nervous systems, regardless of age. When infants choose to attempt new functional actions, early motor cortex activity is diffuse but regionally specific, perhaps reflecting the joint and muscle activity that's also highly varied. With time, intentional efforts to function, areas of activation become more concentrated as infants discover more efficient pathways and bring them under control. We hypothesize that the refinement of cortical activity observed for reaching will emerge also for walking, as toddlers discover how to control their bodies and achieve more consistently their goal of remaining upright. So building on study 2, we expanded to examine input from the prefrontal cortex as well as the cerebellum, which has been shown to be important in adults when learning new skills and when errors are high, along again with the motor cortex. This is exciting because technically, with an FNIRS system, we should be able to monitor the cerebellar activity, which we can't with this system in children and adults. In infants, this tissue between the scalp and the brain is thinner, and the shape of the skull still allows us to place optodes over the cerebellum. As you can see in the images below on the right, we show where we have been placing the cerebellar optodes, and in the middle, the prefrontal cortex optodes. So the same task is done in study 2, but now a new set of participants, same ages. On the, let me orient you at the very top of that top figure, we have the areas that were active in the prefrontal cortex. Moving down, we have M1. And then if you rotate that head image a bit so you can get to see where the cerebellum is, the bottom figure shows you cerebellar activity. As we observed in study 2, as skill and practice increased, the area of cortical activity in all 3 regions also decreased. M1 showed asymmetry as well, associated with handedness emerging. Activations in the prefrontal cortex and the cerebellum remain symmetrically distributed but reduced. When we look at stepping results, we see that similar to study 2, there was an increase in M1 activity at 12 months as infants self-initiate cruising and walking. For the prefrontal cortex and the cerebellum, we saw similar levels of activity in both test sessions, which is a bit puzzling, but the way we have been trying to understand that is to understand that at 6 months, while babies have not been practicing walking, they have been held upright before. And on the treadmill, we are now pulling that rug essentially out from under them. It's moving them into a posture that's not well balanced. So it may be that they're doing is exploring ways. Remember, the cerebellum is also very much involved in controlling our balance. So it may be that they're exploring ways to at least get their bodies back into some state of control. Well, ultimately, the use of science is to, the goal of science, including brain behavior research, is to learn sufficient basic science to be able to test the application to populations that could benefit from these results. So some of the prime candidate populations for pediatric scientists to use brain imaging we've identified as Down syndrome, myelomeningocele, and cerebral palsy. There are others, of course, but with Down syndrome, we already know from birth the diagnosis. It's a genetic disorder, so we can start studying their responses and their brain activity early. It's also a population that we know will have delay in skill acquisition, and that delay increases relative to healthy children over developmental time. And we also know that there's some differences in their brain structures. We know their brain mass is smaller. In particular, the majority of that reduced brain mass ends up being in the cerebellum. So these techniques give us some opportunities, I think, to begin to explore what's happening at the brain level as they're growing and acquiring skills. The middle image is of a baby born with myelomeningocele, which is the most severe version of spina bifida, in which during fetal development, the spinal cord protrudes from the spine, and there's a break in the pathways at those levels, usually lumbar and sacral. What you can see on this baby is scarring tissue over the lumbar area. Within 24 hours of birth, these babies in developed countries like ours will have surgery to replace the spinal cord in the spine and cover it to protect it. It doesn't fix it, but it protects it. We don't know what's happening at that level, at the spinal level neurons, as the babies grow and we try to intervene. FNIRS is a beautiful system because, for us, because we can monitor spinal neuron activity just like we can cortical neuron activity. So it opens up another set of avenues to explore. The child on the right is a child with cerebral palsy. I'm going to talk about that briefly in this next slide. We know that babies born with cerebral palsy, pre or postnatal, for those babies, that pre or postnatal brain injury negatively affects the development of the cortex and the cortical spinal tract. The altered development of the CST is said to affect the delayed acquisition of skilled motor behaviors. We don't know how brain activity differs between those who respond to interventions and those who don't. How do interventions alter the brain activation patterns that underlie the improvement we see in behavioral outcomes? What is the brain capable of doing in different contexts, in real time? And how does it adapt to self-initiated versus imposed practice? Now, I highlighted those first two of what we don't know in green because right now, the design for beginning the experiments to test those questions are sitting in the IRB office at NIH. Ryota Nishiyori and Diane Damiano are waiting for approval, and they're going to get started on asking just those questions. So to summarize, we know a lot about the overt patterns of functional behavior that emerge over the first year of life. We have a growing body of evidence to support the fact that goal-directed practice drives the emergence of these new behaviors and that multiple subsystems contribute to the outcomes. We hypothesize that goal-directed efforts also drive organization of the brain, that plasticity is at work during every phase of brain development, from the nascent phase to skilled performance to adaptation to neural loss. Currently, I would argue, we know a lot more about the brain in decline than we know about the brain as the foundation is being constructed. And I think it's time to change that, and I think we're on our way. Thank you.